So let's remove this more complicated diagram and just show our polar water molecule. And we'll note that this side is a little positive, that's a little negative. Little positive, little negative. Overall, it's still neutral. Overall, there's still 10 protons, 10 electrons. But each side is not neutral on one side or the other. Sometimes I like to imagine this if I imagine seeing the molecules in grayscale, and I give it a color. So if I, for example, said black is positive and white is negative, if I envision what this might look like, so I've got kind of my oxygen and two little hydrogens here like this. If I envision black is positive and white is negative, this would be kind of dark out here, shading to gray, but then light white up here at the negative side. It wouldn't be all the same color of gray. It would have sort of a positive side and a negative side. Compare that to the methane that we had. Remember, each of those bonds was, now three-dimensionally this doesn't actually look like a cross, it's a pyramid, but you get the idea. Each of these bonds was nonpolar, meaning neither side was black or white. So this whole molecule is just kind of gray. Unlike this one, which has a dark and a light side. Now, if we keep in mind that that color scheme represents electrical charge, this molecule has no pattern of charge overall. The whole thing is neutral. But this one is interesting. Because of the way the water arranges, with the two hydrogens kind of bent downward on one side of the oxygen, there's a reason for that, we don't need to get into it right now. The whole molecule together also has a kind of a positive side and a negative side. If these were straight out, well, there wouldn't be any difference, but since they're bent down, this whole side of the molecule is a little positive, that whole side is a little negative. And that is going to make a huge amount of difference. Because now, think about how two water molecules will interact with each other. If I have a water molecule here, and I bring in another water molecule, if it approaches like this, I've got the negative side of one facing the negative side of the other. And like charges tend to repel. So this is a relatively unlikely arrangement. It would be more likely for my water molecules to approach like this, where the slightly positive hydrogen is near the slightly negative oxygen. If they do that, there will be a weak temporary electrical interaction between them. That weak thing there we call a hydrogen bond. A hydrogen bond is a temporary, weak electrical interaction. It's not nearly as strong as a covalent bond or an ionic bond. It's more like a very weak, temporary ionic bond. But even though it's weak and doesn't last very long, it makes a huge difference as to how these things behave. Water molecules have a way that they tend to associate. Now, in liquid water, they're moving around enough that these hydrogen bonds form and break in tiny fractions of a second. But it still means that they clump together. That explains a lot about what water does. For example, have you ever belly flopped into water? Have you ever just dove into water straight down like this and gone whap and felt the water effectively hit you? It's relatively hard to get through the water's surface. That's because of this. Those water molecules are sticking to each other in a way that makes them relatively difficult to separate from each other. That surface tension comes from this. It is also why water absorbs a lot of heat. You can pour energy into water and not change its temperature very much because some of the energy you're pouring in goes to breaking these bonds rather than making the molecules move faster, which is what makes it hotter. That actually affects weather. One of the reasons why coastal cities have relatively moderate temperatures, they don't get as hot or as cold, is because you've got this huge body of water sitting out there that's absorbing heat during the day and then letting some of it out at night. So it keeps it a little cooler in the day and a little warmer at night. It affects the weather patterns over the entire world that water can do that. It's also why ice floats. Unlike most materials, when water freezes, it actually expands a little because these molecules, when they stop moving, like you do when you get into a solid, have to arrange themselves where these things are arranged where the positives and negatives are close to each other, which means they can't be as tightly packed as they are when they're a liquid. So you get a little bigger, less dense, so ice floats. Huge, huge thing. And it's the answer to our question of why some molecules interact with water in an interesting way. So if we know that water is polar, made of polar bonds, and the whole molecule is also polar, then that's going to affect how this is going to interact with some materials. So let's go take a look back at our salt crystal. So back to our table salt. There's our sodium ions. And our chloride ions. So these stick together very nicely. It's very hard to get them apart. But do keep in mind, they're not holding totally still. Imagine each of these as jiggling slightly. So they're popping a little bit away and then coming back because they're strongly attracted to these opposite charges. But what happens if we put it in water? So imagine this sodium ion here popping off occasionally, popping off, coming back, and then we get some water around. Now this is a positively charged sodium ion, so which side of the water will it tend to be attracted to? The negative oxygen side. So now imagine here's some slightly negative oxygens coming up to this. Now my sodium ion, normally it sticks close to the negatively charged chlorides, but here it says, oh, but there's some other negatively charged things. I'm okay getting a little further away because I've got other negatively charged things nearby, so I don't feel like I'm a lone charge out here. So my sodium ion can come a little bit away from the rest of the molecule, from my salt crystal, because it's surrounded by these water molecules. And now some water molecules can get in here and take that sodium ion away from the crystal because it can be surrounded by opposite charges that balance out that positive charge. The chlorine is going to have the same thing happen when it's approached by water molecules arranged the other direction. So all of the ions in my salt crystal will end up surrounded by water molecules and separated from the crystal. This is what's happening when salt dissolves in water. Each ion is stabilized by the polar water molecules, and it can be separated from them so that eventually each ion is out here on its own, surrounded by something we call a hydration sphere. It's not the same water molecules. This one will pop away and another one will come in. They're changing all the time. But at any given time, this sodium ion is surrounded by water molecules with their oxygens pointing in. This chloride is surrounded by ones with the hydrogens pointing in. So each one is stabilized, and they can be separated from each other and still be happy. Does that make a little sense, I hope? So, an ionic solid like this will dissolve very nicely in water. Salt dissolves in water. When you put in that salt and stir it up and it disappears, it's not gone. It's just separated into individual ions, which are now dispersed in the water. If you boil the water, take the water away, the ions that are left will start clumping together and form a film of salt crystals where the water was. Cool. Now, salt's not the only thing that does this, though. What I'm going to draw up now is a molecule of glucose. It's going to be a little complicated. So here's the basic structure. 6 carbons, 1 oxygen here. Each of these carbons is going to have an arrangement like this. Now, it matters which one is whether it's pointing up or down, but I'm not paying much attention to that right now, so forgive me if I get it wrong. Now, I will not ask you to draw this, but what I want you to do is look at this molecule and try to identify where the polar parts are. Remember, bonds between little sisters, between carbon and hydrogens, are nonpolar. So like this bond here, carbon to carbon, that's nonpolar. Carbon to hydrogen, nonpolar. But let's look for the polar bonds, the ones between big and little sisters. So between, there's no nitrogen here, so between oxygen and carbon or hydrogen. Oxygen-hydrogen is always a polar bond. So there's this polar spot. All the oxygen hydrogens are polar. And oxygen to carbon. Not quite as polar as oxygen to hydrogen, but weakly. So we'll kind of put those in. Look at all of those places on here that are polar. Meaning at this oxygen to hydrogen, the hydrogen's a little positive and the oxygen's a little negative. That's a place where water can form a hydrogen bond between the slightly negative oxygen and the slightly positive hydrogen. There's all of these spots sticking around on the outside of the glucose molecule. This is glucose. Where water molecules can form hydrogen bonds, which means water can surround this with a hydration sphere and isolate it from other glucose molecules. Glucose dissolves in water. The more polar parts a molecule has, the more easily it can dissolve in water. So, glucose, which is a part of table sugar, dissolves nicely in water. On the other hand, take a look at this. Butane. Let's see if we can find any polar bonds in this. Carbon to carbon is nonpolar. Carbon to hydrogen is nonpolar. All of the bonds in this are nonpolar. There's no part of this which is a little more positive or a little more negative, which means there's no part of this where water can form hydrogen bonds. So water doesn't know what to do with this. Water can't form any hydrogen bonds with this. It will not dissolve well in water. Oils and fats, as you'll learn about soon, are mostly like this. They are electrically set up so they have few or no places where water can easily form hydrogen bonds, so they can't easily associate with water, as compared to things like glucose, which has lots of polar parts and can. Now, the question often comes up, how many polar parts do you need to associate well with water? For example, look at this one. This is methanol, methyl alcohol. Here's a big polar part. This part is nonpolar. Will this interact with water? As it turns out, yes. Methanol dissolves very, very nicely in water. So does ethanol, grain alcohol, the stuff you find in beer. As does isopropyl alcohol, common disinfectant. But the more of these you add on, the less well it will dissolve in water. By the time you get to 6 of them, it really doesn't dissolve well in water at all. So I can't give you a simple way of deciding, will it dissolve well in water? The more polar parts it has compared to nonpolar parts, the more easily it will dissolve in water. Now, some things even have charged parts. They'll have an atom on there that actually has a full electrical charge, not a partial one like these. That makes it even more associable with water. Charged things almost always do well in water, unless it's a really big non-charged part with one little charged part. So there's a couple terms we use for this. Things that dissolve well in water, like most alcohols or glucose, things like that, we call hydrophilic. Hydro, meaning water. Philic, meaning loving. Hydrophilic things dissolve well in water. They interact well with water molecules. This isopropyl alcohol is hydrophilic. Glucose is hydrophilic. Butane does not interact well with water. The older term people used for that was hydrophobic. Phobic meaning fearing. But that's a little bit misleading, actually, because butane is not actually repelled by water. We'll talk in just a moment about how it actually interacts with water. The more term we use more often now is lipophilic. Lipo is fat. Philic is loving. So butane we would probably describe as lipophilic, meaning it interacts well with fats, which are nonpolar molecules. Fats are composed of lots of stuff like this. There's few places for water to interact, so they tend to be okay with each other, but not with water. This would do better with the fats. So as one of the last things we do here, let me talk to you for just a moment about how hydrophilic and lipophilic things actually interact with each other. All right, let's talk about how hydrophilic and lipophilic actually works. Now, what I've drawn here is a relatively simple version of a triglyceride, which is basically an oil or a fat, like you'd find in food. This one, it would actually be longer than that almost always, but the basic idea is there. Now, take a look at this, and if we look at where might the polar parts be, we see some carbon to oxygen things in this area, here and here. But other than that, it's all nonpolar bonds. So this thing overall is very nonpolar, very water unfriendly. Now, what I'm going to do is instead of drawing it like that, I'm just going to draw it as a sort of a block. It's a big molecule. So here's my big nonpolar block. Let's put that and some other big fat molecules, big nonpolar blocks, in with some smaller polar water molecules. And let's see what they're going to do. Now my water molecules, since they're polar, each of them can be attracted to other water molecules. So they will tend to form bonds with each other. And when things can do that, they tend to form as many bonds as they can. So for example, these two water molecules will stick to each other. And that one will tend to stick to that one. The ones here in between the fats, that can only form a bond here. But if they could get out here, they could form bonds with more of them. So what tends to happen in this case, it's not that the water molecules are repelled by the triglycerides. That's why hydrophobic is maybe not the right way to say it. What they tend to do is try to get to where they can be around as much other water as possible. So those water molecules tend to move out from between the fats. So as they move out, the fats move together. Likewise, as these move out here, these fat molecules clump up. It's not that the fats are repelled by the water. It's that the water is getting out from between the fats, which forces the fat molecules together. This is why, if you put oil and water together, the oil clumps up with the other oil and separates out from the water. That's what we mean by hydrophilic and lipophilic. They don't mix well. They will tend to separate. The water molecules would be unlikely to work their way in here between these. They're much more likely to stay out here where they can bond to other water molecules. On the other hand, if you put butane, one of those small nonpolar molecules in here, it will probably be perfectly happy slipping in there between these. Now there are some more complex things going on here, like van der Waals forces. Those happen more between these fat things, but those are also a kind of a very weak attraction. So it means that if you mix lipophilic and hydrophilic things together, they will tend to separate. The lipophilics will clump with the lipophilics, and the hydrophilics will clump with the hydrophilics. And the hydrophilics will mix in with the water and dissolve in the water, whereas the lipophilics will not. Now, understanding that is actually key to understanding a lot of what we're going to talk about in terms of how cells work. Just as a very, very kind of brief preview of that, if we imagine that life is complex interactions between things dissolved in water, we're going to need some way of separating out some areas from other areas, making sure some things dissolved in the water are here and some things are there, which means we need a barrier in there that things don't cross over easily, that will hold itself together in the water. Maybe something like this might be useful. Now, between that hydrophilic and lipophilic, there's also another possibility, which is something which, for example, if we made a molecule that had a big lipophilic part and then a strongly hydrophilic part, you might get something which would interact with water in one part but not the other. We would call that amphiphilic or sometimes amphipathic. Either term is okay with me. Something which has one part which is very hydrophilic and another part which is very lipophilic. Those will behave in an interesting way in water too. This part will cluster with the water, but this part will not. If you put a bunch of those in water, they'll do something interesting. But we're going to get to that next time. So that's the end of this first lecture. Well done. Hopefully it wasn't too horrible. And I'll see you at the next one.